Okay, so today we'll be discussing ISA, Instruction Set Architecture. So, what is ISA? ISA instruction set is a language set, like set of words which a computer can understand. We can say like we have a lot of people, so everyone will be talking a specific language or few languages. So all those terminologies or words used convey a meaning to us. For example, Hindi, English, whatever. So likewise, every processor knows some language. So what is the language depending on? This language is depending on what the processor's hardware inbuilt hardware or the structure inside. So every word may be adding, it has a kind of a hardware, maybe mostly. This is called the instruction which the processor can understand. So based on all those hardware structures, or maybe or the utilizing all the different hardware structures, we can have combination and permutation of loops or operations, maybe adding multiple bits, maybe squaring, maybe series of n numbers, whatever, logarithm, exponential, lot of things we need process to do. So some of this can be directly accessed by a single instruction, some may be combination of instruction. For example, we can do multiplication by repetition or addition, multiple additions can help us do multiplication. So likewise, this instruction set will give you an idea what the processor can do or what is hardware it is having. Okay. So basically, this is von Neumann architecture where we have uh, we are introducing the concept of stored program concept. Whatever our processor need to do or computer should do it should be stored as an instruction set of instruction which is stored in the memory, right? These instructions are also stored in the memory, as well as while executing these instructions, I may need some data, maybe some numbers or some images, sound, sensors, signals, whatever. So all those also has to be stored in the memory. So this is stored program concept. The program is stored, and each instructions from the program one by one will be executed by the processor, right? So you can see here the stored program concept. Okay, so we have memory here. You can see this memory block where we are storing instruction and data also, and how we are inputting the instructions using some input devices, maybe keyboard, mouse, or maybe joystick, or some punched cards. There are a lot of ways which people use to input them. So these are stored in the memory, right? Maybe initially it may be in secondary memory, the hard disk, right? Right, and then hard disk will give while running. It will go to the high speed memory, fast memory, right? The primary memory called RAM in present computers. Now, when the processor is going to execute, like fetch, decode, execute, processor is always working on these three operations: fetch, decode, execute. While fetching, it fed the instruction, and the control unit will check what is the instruction: is add, subtract, load, store, whatever, any instructions, division also, multiplication, square, factorial. We can have a instruction like factorial also, whatever. So this instruction will be understood by the control unit, and it will be controlling, it will be switching the arithmetic logic unit to use the data from the memory unit and have the operation, execute the operation, division, whatever, and logical operation, whatever, right? And return the result back to the memory, right? So after a series of executions, the result can be seen in the output unit. This can be screen, printer, display, or whatever, LED display, whatever. So this is successful model of a computer. So the concept of von Neumann architecture is all instructions and data are stored in memory, and as per while execution, instruction and the required data are brought into the processor for execution, right? The timely. So who controls it? Control unit controls it. It fetches one instruction one by one, and it decodes it and executes it, right? And all the data are also used in the same time. Now the input and output devices are also required to input the program or data and output, see the output also. So this concept is called von Neumann cortex. It's massively successful. It's a new. It was new in 1950s or 60s. It has changed the revolutionized the computer model, right? Sorry. Okay. Now we'll discuss about what is data path and control path. Um, as we are discussing, you might have seen that two different types of things. One is we are adding two numbers. So the number n1, n2, and the output is maybe result r. So these signals are coming through some path. This is n1 data path, maybe, and this execution, addition, subtraction, all those things. And there's a memory. N1 and n2 are storing some memory, right? So all these paths or all these signal transmissions are happening in generally, let's say in a generally we can term as a data path, data path, data path. Okay? And there are other set of signals which is called, we can say, control, which is controlling the flow of data. That is called control path. For example, we are switching when the N1 is on, when the N1 has come to register from the memory. There is switch 1, switch 2, and which instruction has to be executed. Maybe adder, subtractor, division, ANDing, ORing. So this has to be told to the ALU, and what time output has to be stored. There's another switching here, S3, and it is written back to the memory. So it is read operation or write operation in the memory. Either we are loading or storing, right? And timing, clock. Every instruction, every modules can given the clock for controlling and regulation. So these things are given by the control unit. So that signals are called control path. Okay. Right, so there are two kind of signals: data path and control path. Data path is all the signal data, input, output, instructions, program, and different addition and buses, registers. All this called data path. And other areas which controls, clocks, triggering, enable, right, load, enable, etc. They are called control path. Okay, inside this CPU, there are two paths: control unit and arithmetic logic unit. So all calculations happens inside ALU, right? The control unit generates sequence of control signals to carry out all operations, right? The step-by-step instructions, which units has to be on, triggered, enabled, is decided by the control unit. Basically, we know it is switching using a MOSFETs, is switching on and off, enabling. The processor fetches an instruction from memory for execution. An instruction specifies the exact operation to be carried out, right? Because the control unit knows what is the instruction is saying, what is the meaning of that thing based on your existing hardware, right? So control unit based on its thing. For example, Littleman computer. The best example is Littleman knows it has a small calculator. It has an in basket, out basket, a register, instruction register, a mailbox. It knows that the mailbox address from 00 from 99. So all these things are known to Littleman. Likewise, the hardware features, data path is known to the control unit. So control unit to the control path, or control unit itself is a part of control path, controls the data path so that the instruction is executed. Right? So it specifies the data that has to be operated on. So you can see a program refers to a set of instructions. So what is a program? Program is a collection of instructions which tells computer to do something. Okay, the program refers to a set of instructions that are required to carry out some specific task, like sorting, or maybe summing of a set of numbers, factorial, something. So all those things may be a task, but it can be divided into small instructions. The task can be a program. Although program is a high-level thing, in the sense like it is a abstract, a function can be executed. A program may have a different function which can be executed by different individual tasks. This task can be executed by individual instructions, like that. So this is basically there are two things: data path and control path. So what are the functions of ALU? So we already know ALU has to operate, execute something, and this has to be stored somewhere, some register. So this ALU needs some memory also, right? Okay, so it consists of several registers because we need to store these numbers, and some general purpose, some are special purpose. What is general purpose? Because for storing, and some number n1 I have stored, n2. So all this, there are some general purpose registers where I can put all these numbers as per my problem statement. Okay, and there's a special purpose register. What is special purpose register? We have seen accumulator. There's some registers like accumulator, which what is the specialty we'll see soon. And there are other special registers like memory address register, data register, that we'll discuss. Some general purpose are for general storage. Special purpose has a special function defined. Now it also consists of a circuitry to carry out different logical operations. I think you have known in digital logic, there are adders, half adder, full adder, 4-bit adder, look ahead, carry adder. So all these are different architectures of adder. So all the logical operations of adding, addition is done using ANDing, ORing, NOTing, different gates, shift and shifter, compare, comparator, etc. So all these are part of ALU, different functionalities, different circuits performing these functionals. Okay, it considers addition, subtraction, multiplication, division, etc. So during instruction execution, the data operands are brought in and stored in some registers, right? Because this data is huge. Maybe we are working on thousands of data, so they cannot be simultaneously utilized by the CPU. It needs a lot of memory, very costly affair. So what we'll do, whatever instruction is executed, based on those instructions, those data which I'm instructing, maybe I'm instructing n1 divided by n2, so I only need n1 and n2. These two data I had to brought into some temporary registers. Maybe we had general purpose register or something. We can take it to some general purpose register. Then the desired operation is carried out, and the result is stored back in some register memory. Okay. What are the functionalities of a control unit? So control unit, as we discussed, is going to manipulate or control the executions happening within the data path, data unit or ALU. So control unit acts as a nerve sender because it is controlling and coordinating. That senses the status of various function units and sends control signals to control their states. Okay. So carry out a specific operation. This is addition. R1 is the destination of what? Sum of R2 and R3. R1 plus R2 is going to R1. R2 plus R3 is going to R1. So the control unit must generate control signals to execute this specific sequence. First, the outputs of the registers, which were R2 and R3 stored, has to R2 and R3 has to be enabled. So then the addition operation within the ALU has to be executed. So this will be executed. What execution? Addition. So there are different operations possible. I'm doing addition. So the output of the adder circuit is going to the register 1 because R1 is a destination register, right? So all those has to be enabled. Registers has to be loaded. All this control signals. So these are the functions of control unit. So you can see all this. Each of this unit is data path unit. So all this controlling part of the data path, like enabling, ONing, offing, selecting the operation, is done by the control unit. So when instruction is fetched from memory, the operation is called opcode, right? So whatever operations you need to perform, that operation is called opcode, and that is decoded by the control unit. And for decoding, after decoding, the control signals are executed, right? So what is the control input of control unit? The instructions what we want to perform. This is the control unit. So control unit will decode and understand what is to be done. So output is this control signal, a lot of signals which is controlling your data path. This is the data path. Okay, so now memory subsystem. As we already know, there are two types of memory. Primary memory, which is working memory, as you might have heard about working and non-working memory. This is analogous to our brain. Our brain also has a lot of memory areas where memory is stored. So some part of the memory used for while we are discussing working and learning and all that. So called working memory, right? So although it's not well defined or well researched how brain is storing energy, storing memories and all those things. But in computers, we don't need every data or instruction same time. At the point of time, some data may be required, one instruction may be executed. That is stored in the primary memory for faster. This memory is always slow. There is always a processor memory disparity in performance or then performance gap. So we need to make it faster. So we use different hierarchical layers like primary memory, secondary memory. Secondary memory is very slow for large storage. Large data we can be stored in secondary memory. And this is a bit low memory, small memory, but all the immediate data we need can be stored in primary memory. But it is still slow. It is 5 to 10 times slower than the processor. more than 5 to 20, maybe 100 times also. So these are also used for temporary storage. Then from this primary memory, I'll take two registers, R1, R2, data is going to registers for the immediate processing to the ALU. Then we have to process using ALU. Okay, fine. Now the processor has direct access to the primary memory, definitely, because it needs a high speed memory. And processor, within the processor, registers are a part of processor. That's why I'm not mentioning registers separately here. R1, R2, R2, they are part of processor, internal part of processor. But primary memory, the processor is directly interfacing with. Okay, so that is what we discussed. The memory system has to be implemented in hierarchy level because the performance matters. And then caches are the fastest memory. We'll discuss in later units. And it is divided into closer to the processor is L1, again a bit far from the processor is L2, again farther is L3. So this supports the hierarchical. You can see this is a pyramid-like structure. L1 is the fastest, and L2 is the next fastest. Then L3 is again, size is increasing. You can see as we go down, the size of the memory is increasing, speed is decreasing, as well as this. Again, the cost of is also increasing from bottom to top, or you can see cost is decreasing from top to bottom. And then we have primary memory, then secondary memory. So like this. But processor registers from the top of the pyramid, R1, R2, R3, something like this. So the cost, economy is another important criteria, because we cannot have a high-speed memory with very high storage, with low cost. Because as we increase the storage size, the cost is definitely going to be very high. Ultimately, the process size may increase, so we cannot afford increasing process size because the processor cost is going to increase. So we'll discuss this another time. So these are different types of memory. As you already know, there are random access memory. We have random access RAM, read-only memory for storing the bootloader program. We need some memory to store the address where my OS operating system is stored in the disk or a magnetic disk. So we use a read-only memory. Maybe we have other applications also. And magnetic disk, slow memory, very slow but huge memory. Main advantage of magnetic disk is cost is very less. Cost per bit is means unbelievably less. That's why we are given by all the Gmail, Google servers, Facebook servers, all the social media is giving us a lot of free storage. It will not be possible if there is no magnetic disk. And flash memory is the recent memory. Recently, maybe last 10 years, it has been very famous and very fast. And this also can be also used for substitute for magnetic disk. This day, magnetic disk is substituted by flash memory. And another kind of memory, SSD kind of. I think you have heard about SSD hard disk is coming. It is very fast, solid state drive. Instead of magnetic disk, we are going for solid state drive, right? Advantage is it is going to be less heavy, because magnetic disk is always heavy, because it has a reader, writer, magnetic storage is very sort of cylinders, head, and all those complications. But SSD is solid state, so it can be made very thin and all those things. So flash memory is also, a lot of these things are under research also. Can we have a flash memory for hard disk, something like that? Maybe flash memory and SSD has something to do with, I think. I'm not sure. Maybe some of the SSDs can be used. Flash memory can be used for SSDs also. I think so. Okay, now we have input units. Input units is whatever device or system or thing which helps us to input some data into the computer. Can be keyboard, mouse, plotter, printer, camera, scanner, mouse, or even card readers, all those things, touch screen. Now output unit, this is output screen, printer, projector, buzzer, sound system, plotter, etc. Okay, so instruction set architecture. This serves an interface between the software and hardware, right? So we are talking about the language which I discussed. What the language your processor can understand. That language is depending upon a hardware. What hardware is there which can perform some operations. So based on that, we'll define some instructions. That little man has some things hardware like calculator, mailbox, input, output, baskets, and the registers, instruction register, counter, etc. So based on that, we define few instructions. So that is the instruction set architecture, and it is every processor have an instruction set architecture. So it serves as an interface between the hardware and software. So software code instructions and hardware, it has to be executed on the hardware. So this is the interface between the software and hardware. ISA is the interface between software and hardware. Okay, so the really consists of information regarding the programmer's view of the architecture, right? Ultimately, the hardware has to be utilized to solve our problems. So we have to program it, right? Set of instructions which can execute, solve a problem like algorithm flowchart we already discussed. So this has to be written in a set of instructions. So this is programmer. So the person who is writing the program is called programmer, and he should know the architecture. So based on the architecture, he is going to program. That is called assembly language we are talking about. So we'll be using registers, address bus, data buses. Okay, so what is the number of operands? Operand means the data on which I am working, maybe N1, N2, data stored in this register are called operands. Right, input operands, output operands. So the data is referring to the data on which I am working. Okay, so ISS are not specific to a particular computer architecture. So there are some ISS which are general purpose, or it can be used in many architectures. So we can say many ISS are not specific to particular computer architecture, right? There can be some which can be, because why? Because ultimately, if I make individual ISA for or at least assembly language for individual process, it will be very difficult for user to or a customer to learn every time. Every new processor is a new language or new instructions. It will be very difficult. So we'll make it sure that it is compatible to the earlier versions. So we'll make it compatibility is very important, because ultimately these companies are working for profit. Profit comes only if your product is used by more customers. Customers will use only if it is user friendly. User friendliness means it is you don't need put much effort to learn the instructions, or which you have already learned some instructions of previous processor. We can implement this in here also. So in industry, it means a lot. You don't need to upgrade your systems. It is compatibility. Okay, some instructions have been given here. So in load, store, add, so multiplication. So there is a multiplier. You should know that there's a multiplication unit in the hardware that's allowing you to call this instruction. Division, squaring. Squaring is is nothing but multiplication with same input. And jumping, branching instructions, change of control, interrupt we are not discussed, we'll discuss stop, call, trap. These are different kinds of interrupts. Exponential, logarithm function, output. So these are different kind of instruction. This is part of an instruction unit. So the interrelation between the machine organization and instruction format. There will always a correlation between machine organization and instruction format. Whatever you have, we can offer, right? You cannot offer something which if you don't have a logarithmic thing, you cannot offer it. But if you're offering it, there should be some additional, mechanism with the control unit that it can do logarithm using some existing subtraction, something like that. Okay, so now we are talking about by understanding a high-level language, low-level instruction set architecture formats leads to deeper understanding of computer architecture in general, right? If you read the instruction set of any processor, you can understand what our hardware, what our structures it has in its hardware. Okay, as a computer scientist, understanding computer architecture is more detailed, can build more efficient, reliable programs. Definitely, when you know the hardware, what you're doing, what is the step-by-step instructions, how the data flow is happening, you can definitely write better programs which is more efficient, more faster, less power consuming, and taking less resources also, right? So we are definitely improving so this is one advantage of a hardware engineer and a software engineer. A hardware engineer knows the hardware, so you can write a language specific to that hardware which is most efficient than any other program. But if you write a language in a high-level language like C, Python, or something, it may not be efficient. It may not be efficient because we are not considering the hardware into consideration. Now, the hardware is different for different processors. So We should know idea of the processor architecture, what are the plus and minus of those architecture, which all units are faster, how much time it is consuming. So all this idea can be easily gained by a hardware engineer or a processor or a computer architect. So his way of programming will be the most efficient. So when a computer architecture design phase, the instruction set format must be determined first. Yeah, first it has to be, the format has to be defined first, right? It must match the architecture. Say for example, you have adder, so we should know that what kind of adder it is, 4-bit adder, 5-bit adder, and what kind of architecture. It is a carry look ahead or carry save adder or carry propagate adder. So this whole thing should be understood, how much time it is taking, how many registers it needs, right? So first, the format before design phase, the format has to be understood and it is correlated with the hardware architecture. And it has to be futuristic also. We should think that it has to be, the processor has to in the market for at least 10 to 20 years, right? So you have to be futuristic. A lot of these considerations have to be. So this is example of instruction formats. Number of bits per instruction. So first of all, you should know what should be size of my instruction. Can be 16-bit, 8-bit, and even it can be 8-bit also, can be 1632. So how much is the storage capacity? And this is depending upon how much register size, how much memory size or memory bits can be stored in one location. How many, it also depends on how many bits of numbers you can add same time, subtract, divide, etc. So number of bits in one instructions. So instruction, you should not be consisting of two things. What are the instruction consist of? Opcode and operand. Opcode and operand. You already understood what is opcode? Add, subtract, load, store. That's opcode. Operand means the numbers or the data on which we are working. That means add R1, R2. Maybe R3 is also there. So what is the meaning of this? Into the R1, I'm adding sum of R2 and R3 registers. So what is the meaning? So this is the opcode is add, operand is where data is stored, R1, R2, R3. Okay. So how many express operands per instruction? Say for example, here I'm three operands, R1, R2, R3. But in Littleman computer, we are using one operand, right? Where I'm adding add memory location, maybe add 99. That means I'm adding a number stored in the location 99 with the number in the calculator screen. So it has only one operand or one memory operand, you can see. There are some instructions which have only two operands, maybe add R1, R2. What is the meaning? Maybe it means that the result is R1 only and sum is R1 and R2. Data stored in R1 is added to data stored in R2 and answer is going to R1 only. So it depends. Number of operands. That is the meaning of number of explicit operands per instruction. Can be 0, 1, 2, 3. And the operand location. Operand location instructions can be classified. Operand location. Where the operand is located. It is in memory or it is in registers or it is in which area. Right. Stack, queue. Right. They can be register to register operation, memory to memory, and register to register to memory, and types of operations. Memory operations are the data transfer operations are the arithmetic operations are the logical operations, the control operations are the right. For example, halt. Halt is a stop instruction which needs a control support also, called machine control. So there are different types of instruction which needs memory access, control access, etc. Type and size of operand. That is another important thing. This R1, how many bits they are? Is it 8-bit or 16-bit or 32-bit or 64-bit? So this also matters. And how much addresses, how many registers are there? There are R1 to R100 registers are there. So how to access them? With there are 100 things, how many bits I need to access them? Log 100 to the base 2. I need at least 6, 2 6 is 32, 64, yeah, 7 bits. 7 bits I need. So like that. These things we'll discuss also. Now, instruction formats. So here, the design phase we have to think about instruction set format. right? So it depends on a lot of things. We know that Littleman computer has a memory mailbox, which is a mailbox. It has a specific number of locations. It starts from 00 and 01 till 99. So it has a size of the location memory is also important, and how many numbers it can store in the specific mail location. Maybe 1 2 3 I can store, because three digits can be stored. So these are the specifications also are important. How many digits can be stored in the memory location, how many locations are there, 100, etc. So this also depends upon space of the program, how much complexity, instruction length in bits, total number of instructions also important. So all these things also depend before deciding which format I should use. A new format you can design also, it's up to you. So these are the consideration before what kind of problems you are going to solve, kind of. So as we are rightly, this is just an add-on slide to last we discussed the instruction length, whether it is short, long, or variable instruction, and memory organization, where is byte organized or bit organized, or it is in a nibble, 4 bits, etc. Stored in memory, or the memory words, how it is assessed, and number of operands should be 3, 2, or 0, whatever. Number of addressable depends upon the processor architecture. How many registers you have in them, how many are general purpose, how many are special purpose, and addressing mode. That is another important, very important part of a computer architecture, addressing modes. Okay, so 1 minute, we'll take a call. Hello. Sir, can I call you? Okay, I hope I'm audible. So addressing mode is a very important part, like how these operands are accessed from the memory and how they are stored back. Basically, you can take it from memory, you can take it from register, or you can take it from stack, and how you're addressing that thing, how you're addressing your registers, how you're addressing your memory. So that is addressing mode. So we'll discuss maybe later. Okay, so now we'll see the architecture, specifically different architectures, which is very commonly used. We'll discuss that. So, so architecture design is how this CPU is going to store the data. Okay, so we have stack-based architecture, accumulator-based architecture, register memory architecture, general purpose register architecture, etc. We'll see all those things. So as the name states, you can see in stack base we have a lot of memories in the stack. Say, yeah, so, you know stack. I think you have heard of stack of books, stack of plate. I'm keeping a lot of books one over the other. I'll see the stack of books, right? So the top book is here, so which is first out, which book can be output first, top book. So you can see last in, first out. So this memory data structure where the storage is happening in last in first out mode is called stack of plates, stack of books. So this is stack architecture where my data is stored like this. So whatever is need to processed by the ALU has to be taken from the stack. Result also has to be put in the stack. That will coming in the top phase of the stack. As stack goes on, more data is going to accumulator over it like this. So this is stack based architecture. We'll see it. Accumulator based architecture is most common. So we have an accumulator which can do a lot of processing, and data has to be N1 and N2 is going to the accumulator, going to the ALU, and we have one storage, or we can say accumulator is that register which stores the result as well as it is giving the input to the ALU also. It can be drawn like this or it can be drawn like this, accumulator based architecture. This is your adder, and the result is going back to the accumulator, and this other operand can be coming from memory or register. We'll see. And register memory architecture is also that also we'll kind of see. Now let's see the stack based architecture. So this is stack based architecture. You can see only important point here is all the data is coming from the stack. This is the top of the stack, top top of stack, then it is as it accumulates, more data is coming on the top of the stack. So whatever ALU is processing is coming from the stack only. Whatever result ALU is putting is also going to the stack only, right? And there will be stack pointer, which always point to the top of the stack. So this is a kind of stack architecture. So the instructions will be like this: push X. That means you're putting X into the stack. Then push Y also into the stack. That means we have X and Y in the top position of the stack. X is here, Y is here, and other locations, other data is already in the bottom. Now add means top two things from the stack is taken to the header unit, and the result is also going to the top of stack, something like this. That means the result is again in the top of, replaced in the Z is here, top of that. X plus Y is replaced in the top of the stack. Now it is pop. Pushing means inserting into the stack. Popping means inserting out of the stack. So the result is X plus Y. Z equal to X plus Y is inserted or ejected to the output unit. So basically, there's a lot of stacks. ALU is taking inputs from the stack. Output is also stored in the stack. So there's a stack architecture. So basically, thing is last in, first out. Okay, stack cannot be accessed randomly. There's a specific kind of structure and way of accessing it. So also there are some architectures. So right now we'll see most common architecture is accumulator-based architecture. So this is the accumulator-based architecture, which we discussed. So here we can see there is a register, common register accumulator, which is storing the data which is before execution. Data is going to the accumulator, and after result, this data is again stored in the accumulator, right? And the other operand is coming from some other memory, some other register, or some other locations, right? But one operand is always in, for example, R1. Data R1 is in accumulator Y1, and R2 is coming from some other area, and result R1 plus R2 again going to accumulator. So this is what Littleman concept also. This is the, you can see the calculator screen principle. This is the calculator. Again, the result is in calculator screen. This is the calculator screen in Littleman. Calculator screen, accumulator. So first we have to load X. Load X means from the memory, I'm putting data into the accumulator. Then add Y. Like Littleman, the Y is taken from the memory. Y is coming from the memory. It is added to the value already in the accumulator, and the result is already in the accumulator. And store in Z. That means result in accumulator is stored in the location Z. So this, you can see how the hardware changes, the structure of the hardware changes, the instructions is also changing. In previously we have push, pop, and add, all those things. But here we have load, store architecture based on the accumulator-based architecture. The problem is it is very slow, because for every operation we have to operands has to be loaded from the memory one by one. So it's very slow. Again store it back, again next operands, again store it back. So it will be slow. You can see in the Littleman architecture, it is not as friendly as in high-level programming or in some other languages, because we are directly working on the hardware. There is no in between compilers to make it fast, or automation is not there. So all instruction here, all instruction is one operand, and yeah, two operands are there. One operand is already in the accumulator. The other is also coming from the memory or other register. Usually memory, especially in Littleman. Okay, in accumulator architecture, one operand from binary operation is implicitly in the accumulator. Without, you don't need to specify that. It's already in the accumulator. Littleman, Mary will discuss in upcoming lectures. But the problem is creating a lot of traffic. It is slow. A lot of memory load store architecture is used here also. Now this is register memory architecture. We can see the input is directly taken from few registers. Instead of accumulator, we have a set of registers. Maybe it is called R1, R2 till Rn. So the input is going from one register, and another input operand is going for another register. After addition, going to another, output is going to another register. We can see this is like R1 plus R2, R2 plus R3 something. So we can say add R1, R2, R3. This kind of architecture is called register memory architecture. Can be also okay. This not register memory architecture because one operand is coming from register, other is coming from memory. That is why it is called register memory operation. Sorry, yeah, I'm sorry for that. Because we can see one operand is coming from the memory, another is coming from the register. Okay, and result is also going to memory. You can see the result is also going to memory. No, this is also going to register. Yeah, it's going to R2. The result is going to be going back to some registers. You can see here. And this there can be a lot of variability based on your application or specific thing you are trying to do. There are a lot of options. This is up to the computer architecture to decide which architecture you need to solve. So one of the operands is in register, another is in memory. At least one operand should be in register. That's the only condition. Now register to register, you can say register to register. It is fastest because you can see input is coming from the register, output is also going to the register. This is faster. Why is register is fast? So that is quite fast. You can see load first. Initially we have to load the register first. That is the only problem. Two numbers has to be loaded into register R1 and R2. Then we have instruction. You can see add R1, R2, R3 or R3, R1, R2, right? And the output is after the output is stored in the R3, then it can be taken from the R3 to the memory. So we have 4 instructions here. First loading R1, again loading R2, then adding and storing 2. So this is register. Fastest, quite costly because we need a lot of registers. Lot of registers means lot of chip area, processor area. Increasing processor area will reduce the profit because number of processor per yield or processor per manufacturing process is less. So definitely companies, the cost will increase. If the processor is small sized, we can have maybe 50, 60 or even hundreds of processor within one fabrication or one silicon wafer. This is a silicon wafer. Here we design all the uniform chips. So these are all chips in the one process. If area is increased, we can say number of process per silicon wafer is decreased, right? So the profit decreases. And profit decreases, the cost of the processor increases. So that is just a connection between the profit and the process size. This is faster and converter stack based on efficient implementation also is possible using compilers or high level languages. Results are longer instructions, yeah, because we have add R1, R2, R3 is lengthier. So most systems today use GPR because of their efficiency, easier programming, and compilers are complicated. Advanced compilers are available, so we can do. Now special purpose registers. So this is another topic. I think we don't have time for discussing this. Especially memory operation MAR and MDR, where address is stored. Suppose we want to access some data from the memory, from which address the data has to be accessed. That has to be stored in memory. Address is MAR, and this temporary data which is to be accessed is temporarily stored in MDR. This is happening in the case of loading, storing data, right? So whatever data, right now I'm giving an example of loading or receiving or retrieving data. So whatever data has to be retrieved will be temporarily stored in MDR. The address from which we need to retrieve will be stored in MAR. That is for reading. For writing, the data which need to be written is stored in the MDR. Which address had to write it is stored in the MAR. So this will be discussing about in the next coming class. So this is especially used in all the processes. Okay, so that much for today. Tomorrow we'll discuss more about MAR, MDR, how the instructions are executed, and program counter, instruction register, etc. So some simple instructions also we'll discuss. So I think if I'll stop recording, and if any doubts, I can take.